Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Today, we're going to talk about a really important internet security topic, but we'll explain it in a way anyone can understand. Let's start with an analogy. Imagine the internet's domain name system, or DNS, works like the postal service. When you want to visit a website, you're essentially sending a postcard asking for directions. You write the website name, like www.mybank.com, on the postcard and send it off. The Postal Service, or DNS, writes the physical address, the IP address, on the back and sends it back to you. The problem is, this is all done with postcards. Anyone can read them, and more importantly, anyone could potentially intercept your postcard and write a fake address on the back. You would have no way of knowing you're being sent to the wrong place. Let's visualize how this fake address trap works. In the tech world, it is called DNS cache poisoning, but the concept is simple. You want to go to your bank's website. Your computer asks your internet provider's DNS resolver, "What is the address for mybank.com?" A criminal, listening in, sees your request. Before the real bank's response can get back, the criminal quickly sends a fake response that says, "Oh, mybank.com. That's at this other address," which points to a fake website they have set up. Your resolver, without a way to verify the information, gives you the fake address. You go to a website that looks exactly like your bank, you enter your password, and the criminal steals it. This is one of the most dangerous types of attacks on the internet because it is so hard for a normal user to spot. DNSSEC was created to stop this exact problem. So how do we fix the postcard problem? We need a way to make sure the address on the back is legitimate. DNSSEC is the solution, and the best way to think of it is as a digital notary service for the internet. Imagine instead of a postcard, the response comes back in a special, tamper-proof envelope. This envelope has two key features. First, it has a wax seal that proves the contents haven't been opened or changed. This is for data integrity. Second, the seal is stamped with the official, verifiable stamp of a trusted notary. This proves the letter actually came from who it says it came from. This is for origin authentication. DNSSEC brings this exact concept to the digital world. It doesn't hide the data. The address is still visible, but it provides a way to prove it's the correct data from the correct source. Let's talk about that first part, the tamper-proof seal. In DNSSEC, this is called a digital signature, or an RRSIG record. How does it work? The owner of the website, like mybank.com, uses a secret private key, a long, secret password, to generate a unique digital seal for their DNS information. This seal is mathematically tied to the data itself. If even one character of the data is changed, the seal breaks and will no longer be valid. It's like a wax seal that shatters if the envelope is opened. So, when your resolver gets a response, it also gets this digital seal. It can then perform a check to see if the seal is intact. If it is, the resolver knows the data hasn't been tampered with. But that leads to another question. How do we know the seal itself is legitimate? A seal is only trustworthy if you trust the person who made it. This is where the second part comes in, the notary's official stamp. In DNSSEC, this is the DNS key record, which is a public key. While the website owner has a private key to create seals, they also publish a corresponding public key that anyone can see. This public key is like the notary's official stamp design, which is listed in a public registry. This key has a special property. It is the only key in the world that can verify seals made by its matching private key. So, your resolver gets the data and the seal. It then looks up the public key for that website. It uses this public key to check the seal. If the key validates the seal, the resolver now knows two things. The data was not changed, which confirms its integrity, and it was sealed by the true owner of the private key, which provides authentication. Okay, so we can use a public key to check a seal. But this creates a new problem. How do we know we have the right public key? What if the attacker gave us a fake public key along with their fake data and fake seal? It would all seem to check out, but it would be a complete fabrication. This is the core problem of trust online. You can't just trust something because it says it's trustworthy. You need to verify it with a source you already trust. We need a chain of command or a chain of trust. We need to be able to trace the trustworthiness of any key back to a single source that everyone in the world agrees is legitimate. The internet solved this problem with a hierarchy. Think of it like a global company. At the very top, you have the CEO in the DNS world. This is called the root. The root is the ultimate source of trust, and all our computers are pre-programmed to trust the root's public key. It is our starting point, our trust anchor. The CEO, the root in this analogy, doesn't manage every employee. They manage the vice presidents. In DNS, these are the top-level domains like .com, .org, or .gov. The root uses its unbreakably trustworthy key to sign off on the public keys of the vice presidents. This is like the CEO writing a memo saying, "You can trust these vice presidents." Then, the vice presidents, like .com, sign off on the keys of the department managers they oversee, like Google.com or mybank.com. This creates a perfect, unbroken chain of trust. To trust mybank.com, you check with its boss, .com. To trust .com, you check with its boss, the root. And since you already trust the root, you can be sure the entire chain is secure. Now, if you were a bank, would you use the same key that opens the front door to also open the main vault? Of course not. The more a key is used, the more risk it has of being lost or stolen. DNSSEC applies this same logic by using two separate keys for each domain. First, there's the zone signing key, or ZSK. This is the daily use key. It's the key used all day, every day to put the tamper-proof seals, or the RR-SIGs, on all the regular DNS data, like IP addresses. Because it's used so often, it's considered less secure and is changed frequently. Second, there's the key signing key, or KSK. This is the master vault key. It is extremely powerful and has only one job: to sign the other key, the ZSK, by signing the ZSK. The KSK is essentially saying, "I, the master key, certify that this daily use key is legitimate." The public part of this KSK is what sent up the chain of command to be notarized by the parent domain, like .com. Since it's so important, the KSK is kept very safe and is rarely used or changed. One last problem. What if a criminal tries to trick you about a website that doesn't even exist? They could intercept your not found message and replace it with an address to their malicious site. DNSSEC solves this with a clever trick, which we can call the filing cabinet method. Imagine all the websites in a zone are in alphabetically sorted folders in a cabinet. If you ask for the folder for xwebsite.com, and it doesn't exist, the server can give you two things: the folder for website.com and the folder for your website.com. By showing you these two folders, it proves there is nothing in between them, so xwebsite.com cannot possibly exist. It's a verifiable proof of a negative. The modern version of this, DNSSEC 3, does the same thing but first scrambles the folder names using hashing so criminals can't just read all the names and see every website a company owns. It proves the gap exists without revealing the names of the folders around it. Let's put our entire analogy together and walk through a real request from start to finish. You ask for www.mybank.com. First, your resolver, trusting only the root, the CEO, asks it, "Can you vouch for the key of .com, the VP?" The root gives back a signed memo, ADS record, confirming the .com key is legitimate. Next, your resolver then goes to .com and asks, "Okay, I trust you now. Can you vouch for the key of mybank.com, the department manager?" The .com server gives back another signed memo confirming the bank's master key, its KSK, is legitimate. Now your resolver goes to the mybank.com server and says, "I have proof your master key is real. Give me the IP address for www and also your public keys." The bank's server returns the IP address, complete with a tamper-proof seal made by its daily use key, the ZSK. It also sends a list of its keys, with a seal made by its master key, the KSK. Your resolver performs the final checks. It confirms the master key is the one .com vouched for. It uses that master key to confirm the daily use key is legitimate. Finally, it uses that daily use key to confirm the seal on the IP address is intact. Only when every single step in this chain is perfect does it send you to the website. If any step fails, it protects you by showing an error. So, let's bring it all home. What does this mean for you, the everyday internet user? You can think of DNSSEC as a silent, digital bodyguard that's working for you every time you browse the web, provided your internet service provider uses it. It ensures that when you type in a website address, you're connected to the real website, not an imposter. It protects you from the fake address trap by using a system of tamper-proof seals, or digital signatures, and a strict chain of command for trust that starts at the very top of the internet. It's one of the most important, yet invisible, technologies that makes the internet a safer place for everyone to conduct their business and live their digital lives. Thank you for your attendance. Please consider subscribing to the channel.